Lab 5, Motion Prediction by Shervin Praveen. The purpose of this lab is to show the accuracy of a computer model. We will use David Scott's experiment on the moon on the Apollo 15 mission. We will be using GlowScript and Newton's laws in our lab. The main physics ideas. We use the Newton's second law, which is used to demonstrate the forces present and is shown by F net equals ma. We also use the velocity and position update formulas, which are used to calculate the velocity and positions during each delta t. Experiment analysis. In this lab, we will be analyzing David Scott experiment, where he drops a feather and a hammer on the moon. In his experiment, the feather and hammer reach the ground at the same time. Tracker modeling. We choose the system to be the feather or the hammer, and we choose our surrounding to be the moon. Initial conditions. The objects are placed some height above the surface of the moon and released from rest. We use Tracker to follow the motion of one of the objects during its fall. Note, we only need to model one of the objects, since in the video they fall at the same rate. Coding. Initial conditions. The objects are placed some height above the surface of the moon. We set this point to be our origin, to calculate the distance the objects had to travel. We use the acceleration on the moon, which is around 1.62 meters per second squared. We then use our update formulas to calculate our position and velocities until 1.15 seconds have passed, which is the time it took for the objects to reach the ground. In our code down below, you can see we set g equal to 1.62. We set f-grav to only affect the y direction, which is -1 times the mass times the gravity. And down below are our velocity and position update formulas. As you can see, we didn't have to specify if we use the mass of the feather or the mass of the hammer, since in the velocity update formulas, we have f-grav over the mass, which cancels out the masses, so we're only left with the acceleration. This shows that the masses of the objects don't matter, and we will talk about this later. Results. Based on our results, we find that we are near perfectly able to predict the motion of our objects. The model is also able to find the height the objects were dropped from, which is around 1.1 meters high, or 3.61 feet. Questions. The model's accuracy. The model is so accurate because the experiment was conducted on the moon. This takes out the variable of air resistance. The objects were also dropped from rest, so there was no initial velocity we had to calculate. What if the object had more or less mass? We notice in the experiment both the feather and hammer fell at the same rate, even though they have different masses. This points to the idea that mass is not a factor in the speed of an object's fall. The proof also comes from our net force being only gravity. So we start off with F net equals ma. Our F net in this case is just the force of gravity, so we have mg equals ma. We can cancel out our masses, so we're only left with g equals a. Would a feather and hammer fall at the same rate on Earth? Not exactly. The reason the feather and the hammer fell at exactly the same rate was because on the moon there is no air to provide resistance. On Earth, the feather is more prone to air resistance because of its cross-sectional area coupled with its low density. Thank you.